Hey everybody, I'm back. Sorry I've been away, but I have some news. So you might notice I have a new microphone, so it will sound a little better. Another new thing is I have a drawing pad, so you'll be able to see my amazing handwriting. So prepare yourself for that, and let's just get right to it. This is Leetcode 11, container with the most water. And essentially given a bunch of containing walls, return the max amount of water that can be contained within it. So area just being width times height, In this example right here, the most that can be contained is, let's see, it's 7 wide and it's 7 tall because this wall is the shorter of these two, and the water can only go that high. So given a bunch of wall heights, return the maximum amount of water that can be held in between them. And no creative solutions like slanting. Just ignore that kind of stuff. So yeah, for this example, given an array of heights, you would output 49 because it's 7 times 7. So let's first list out our assumptions. So first things first, I would say we will actually have to visit every single wall that we are given. Because for example, we're going left to right or something like that. We were checking the first two and we're moving to the right. If we had two walls of 800 height, then we would have to visit them. Otherwise, we could be potentially missing on a best answer. So I'm going to say it's going to be at least O of n, meaning that we're going to have to go through each one once. The second assumption is that we're going to have to keep track of the most area over time. So, something like max area. And then what are other assumptions we can make? Let's see. I mean, we could just come up with the formula for what the area is given any two things, or given two heights. It would just be the minimum. So right here for the example, would be the minimum height times the width equals area. And so now, okay, so we can calculate that for every single pair. So you could go into some more edge cases, but I think that's good for now. I'm going to say that, first solution. How about we just compare every single two pairs? So these two pairs, and then this pair, and then this, and so on. And then once you've gone through all those, we compare this, and these two, and so on. And so that would be O of n squared, because you're visiting n pairs n times. So that's one way, but I think that that's unnecessary. And I think that we can come up with a better solution because by basically shrinking our search space. So what are some ways of doing it? So here's a couple right off the top of my head. You could start at the middle and, compare this and, calculate this area, and then choose the better candidate to the right or the left. But I think it's actually more intuitive to start at the edges and move in, and then continually remove the worst candidate. So here it might go something like this. You're looking at the input of 1 and 7. this is our max area, right? So you calculate the area, and that's let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 1, so you're going to say, we would say 9. And then now we need to decide whether we go in here and we remove this candidate or the other way. So we're going to be comparing these two somehow. And I would actually argue that the lower height is a worse candidate. That is the worst possible candidate in our set of 2. So if we just eliminated that, now we're comparing these two. And we calculate the area, we get 49. And then we realize this is the worst candidate right here. So we move that, and we move our right bounds over. Calculate this area. Oof, ignore that, that line. And so on until, we remove this one, go to here, remove this one, go to here, until we move, eventually, we calculate this very last area. So every iteration, we're removing 1 from the set until we meet in the middle. So it will be O of n, runtime. And then as for space, I'm going to argue it would actually be constant space, because we only really need to keep track of the heights of every iteration. We only need to keep track of of 2 heights and the best area, and that won't grow. So I think we have an algorithm. Let's write code. So we knew, let me get it a little bigger. Let me know in the comments if this is big enough. We're going to have our max area, and we're just going to start that at 0 because negative area doesn't make any sense. And at the end of our function, we're going to be returning that. So what was our algorithm? So we went through, we started at the right and the left. So let's define those. So I'll just say left equals 0 and right equals the length of this very last index right here. So it would be height dot length minus 1. That might be size, but we'll see in a sec. And then we could do a for loop or a while loop here. I'm thinking while is just simpler, even though we know how many iterations there are going to be. I'm just going to do while, and I'm going to say while left is less than right. And then we just have to be sure at every single iteration to either increase left or decrease right. So I will say if something like this, else decrease right or increase left. And then, so what are we doing? So at every iteration, we're calculating the max area, or we're calculating the current area. So let's see, int area equals, let's see, whatever the leftmost height is. So height at left times height at right. Or let's see, no, it'd be the width. So times right minus left. And you might say, what's wrong with that, Blake? It's like, okay, yeah, I get it. I wrote a mistake. It's going to be the minimum height. So it's either it's going to be the height of the left and the height of the right, whichever one is smaller. And then we also want to update the max area. Max area equals just whatever's bigger. So area or max area. And then what are our cases here? So if let's see, at what point do we want to increase our left? So that's if this is smaller than this. So if height at left is smaller than height at right. And in all other cases, we can decrease. So like if they're the same, for example, oops. If these are the same, we will just shrink the right side. And at the end, we return the max area. Let's see if this compiles. Okay, good sign. And looks like we're good. So that's container with the most water. Until next time.